We go. Should be recording. Okay, and then let me hand over the floor to Group 11.
Hello, welcome to our presentation. We are Design Group 11. My name is Connor Murray, and I'm accompanied by Jose Camacho, Kevin Cochran, Connor Duffy, Matthew Liffrig, Dante Mara, and Alden Zamorano. Today, we would like to present to you Solar, the self-orienting light reflector. Solar is a small-scale heliostat module comprised of 4 identical heliostats, all mounted on a single support structure. Today, we'll be talking to you about the motivation behind our design, followed by an in-depth look at each of our 4 subsystems. Then we will move on to the overall cost. Finally, we will conclude our presentation with a summary of the unique features of Solar. The motivation behind our final design came from a few simple aspects that include our team's passion, greatest skills, and financial drive. We decided our design would be as simplistic as possible through a high degree of modularity while maintaining cost effectiveness and producing the maximum amount of power possible by eliminating interference. I will now hand it over to Kevin Cochran, who will give you an overview of Solar.
Thank you, Connor. So for our design, when we were designing this, we came up with 4 subsystems to go forward. And those subsystems were the mirror and bracket, the rotational device, the modular support structure, and then protective casings. And we did this because these were the key subsystems we believed would make our device successful. And so if you look at the image on our screen, you can see that the whole design measures roughly 2.65 meters by 0.25 meters with a height above ground of 0.8 meters. And so we have 4 individual modules with each having individual rotational axes for both the elevation and azimuth tracking. Each module is bolted into the steel support structure, and then attached to and within each module is an individual mirror that measures 0.25 meters squared. And then we have the rotational devices on top in a single all-encompassing electrical box. To dive a little deeper into the overview, we have this image here with some callouts. So to begin with, the mirrors and the brackets. We use square flat plate plexiglass with solar reflective foil. Each mirror is 0.5 meters in both height and width for an area of 0.25 meters squared. So the whole module has a total reflective surface of 1 meter squared. Attached to the mirror is the rotational devices. Each rotational device is a worm gear driven by a stepper motor connected to a shaft. On the lower end, the lower casing, is the azimuth tracker, and then on the upper end is the elevation tracker. These are bolted into the welded steel frame, which is secured to the ground via wedge anchors that we have buried into concrete frames. The electrical box houses 1 express if ESP 8266 and 8 individual motor drivers so that we have individual control of each motor so that we can have different angles on each of these individual modules for higher accuracy and more efficiency. Protecting each of these components is protective casings on the rotational devices. So we made these out of vacuum molded ABS plastic that seals it off from the environment for longer lifespan. I would now like to pass it off to Jose Camacho to dive a little deeper into the mirror and the analysis we conducted.
Thank you, Kevin. This is the mirror subsystem of our heliostat module. The image shown is a view from the back of the mirror showing the support bracket and where it attaches to the mirror. Each module needed to incorporate between 4 and 16 mirrors with a maximum collective surface area of 1 meter squared per module. The mirror material must have been able to withstand 500 psi of deionized water for the purpose of cleaning each of the mirrors. Each module must be able to reflect 1,000 watts of thermal irradiation to the central receiving tower and provide a total solar concentration ratio greater than 1,000. This again is a back view of the mirror subsystem. The actual mirror is the lighter shaded region in the back of the image. Each mirror is square shaped with a reflective area of 0.25 meters squared, with a total of 4 mirrors on each heliostat, giving a complete area of 1 meter squared per module. The mirror is made up of 2 main components. Solar reflex foil is a reflective material with a protective sheet of plexiglass over top of the solar reflex foil. The foil is attached to the plexiglass using E6000 adhesive, as well as an additional support from the screws used to mount the bracket. The entire module, composed of 4 mirrors, will be able to provide the central tower with about 1,094 watts of thermal irradiation. The plexiglass will be able to withstand cleaning procedures with a strength of 20.39 MPa and a Mohs hardness of between 3.5 and 4. Unlike regular glass, which we had in our previous design, plexiglass has a higher impact strength and is easier to attach using bolts. The support bracket is made from ABS plastic and attaches to the mirror using 4.5 millimeter bolts on each corner of the square mirror. The heat expansion rates for plexiglass and ABS plastic are very similar, which would eliminate any in-plane forces on the screws on either material. The bracket design was created to reduce weight while still providing the mirror with sufficient support on all ends. The bracket design uses a shaft with collar and set screw locking mechanisms to allow the motor to rotate the mirror in the vertical direction while tracking the sun. These images show the exploded view of how the mirror and the rotational shaft are attached to the support bracket respectively. The calculation for thermal irradiance reaching the central tower was found using the radiated flux from the sun to the earth, the area of the mirror, the reflectivity of the solar reflex foil, and the transmission efficiency of light through plexiglass. The strength of the mirror was calculated using the fracture toughness of plexiglass and a specified initial crack length. The total weight of the mirror was found using the volume and density of plexiglass and gravity. Now I will pass it on to Alden to cover the rotational device.
Thank you, Jose. As you can see here on the left, we have an isometric view of both the azimuth and elevation tracking devices, the azimuth device on bottom and the elevation device on top. To the right of this view are the customer needs to be met by the subsystem. Rotational devices are expected to be able to reflect light up to a 100-meter tall tower without exceeding optical losses of 40%. The rotational range of the azimuth tracker should be greater than 150 degrees. And the elevation tracker should be able to rotate up to 90 degrees from a starting point of 10 degrees. Parts within each tracker are off the shelf or are custom made at equal or lesser value. Driving mechanisms are composed of cheap electrical motors that provide the actuation about each axis, and they must be able to connect to a standard 110 to 120 volt grid with the ability to withstand the environmental conditions of the Nevada desert. Both of these tracking devices utilize a worm gear drive in combination with the NEMA 17 stepper motor in order to rotate their attached subassemblies. The azimuth tracker is used to rotate the elevation tracker about the vertical axis of the azimuth shaft, and the elevation tracker is used to rotate the reflective surface about the horizontal axis of the elevation shaft. The worm gear drive is composed of a high carbon steel worm and a brass worm wheel and has a stage ratio of 40:1 to increase the tracking accuracy of both devices. Steel worm is attached to the rotor of the NEMA motor to allow for actuation, yielding a full 360 degrees of rotation about the vertical axis and 180 degrees of rotation about the horizontal axis. The keyed shaft that is locked into the azimuth worm wheel is provided with a bearing underneath and a snap ring to yield both rotational and distance locking of the shaft, and attaches to the top assembly by use of a welded collar and set screws to allow for easy on-site assembly. Within the elevation tracker, the steel worm is subject to higher loads than that of the azimuth tracker due to its vertical orientation. Therefore, both the welded support and the bearing are used to protect the motor and worm shaft from these higher loads. The wind loads that act on the reflective surface are transferred to the connected elevation shaft, which is locked within the top worm wheel. So similar supports and bearings are used to brace the elevation shaft as well. Here are some of the calculations we used in designing the tracking devices so that they may meet the previously stated customer needs. Bottom left image shows the exploded view of the elevation tracking device. The rightmost image shows the exploded view of the azimuth tracking device. First design calculation is concerned with finding the tracking accuracy of both devices. First, the motor resolution was found using the 1/4 microstepping feature of the NEMA motor to increase the steps per revolution of the motor. This value was then used in combination with a worm drive ratio in order to determine the total output resolution of the rotational devices, which then yielded a tracking accuracy of 0.0225 degrees per step, which is nearly 20 times the required accuracy as stated by the customer needs. The next calculation was used to determine the efficiency of the gears, which is equal to 75% as seen below. And this value was found to be well within the range of efficiency of other commonly used worm gear drives. Final calculation was used to determine the design factor safety of the worm gear, which is found to be 1.36 using the Lewis form factor equation for maximum allowable stress. I'll now pass it on to Dante to go over the modular support structure.
Thank you, Alden. To the left, you can see an image of our modular support structure. Based on the customer needs, the modular support structure was required to have a factor of safety greater than 2, a maximum allowable interference of 30%, a total area to reflective area ratio less than 4 meters squared, and be designed to mount on a flat surface. The support structure is the frame on which the rotational device and mirror are mounted on. It's constructed out of 1 inch by 1 inch welded steel tubing. We opted for welded steel frame because of its high strength and ability to be easily welded. Because it is entirely welded, means that there's no on-site assembly other than bolting it to its pre-laid flat concrete foundations, which use the concrete wedge anchors. On the bottom left of the image, you can see the square electrical mounting box. In this configuration, the technicians have easy access to all the electrical components if repairs or maintenance is required. So here we did a shear and bending moment analysis on the structure. I'll take you through the calculations here. Each mirror and rotational device is about 33 pounds. A sum of the forces in the y direction yielded reaction forces of 0.294 kilonewtons. So the maximum shear force on the structure is about 0.3 kilonewtons. Then the normal stress was found using the sigma A equals my over I equation, where the max bending moment was found to be about 0.07 kilonewton meters, sorry. And we found that from the bending moment diagram on our left here. And I is the moment of inertia of a rectangular tube. This led us to our final solution of 60 megapascals for the maximum stress the support structure experiences, which is much, much less than what a hollow steel tube of this size can withstand, which is about 80 gigapascals. This gives our support structure a factor of safety much greater than the customer needs of 2. I'll now pass it on to Connor. He'll tell you about the electronics box.
Thanks, Dante. Let's get into the overall electronics that is used in our design, not including the motors, that is. So as you can see, there's limit switches, motor drivers, and the singular computer. Focusing on the left image within the rotational device, you can see where we plan to use limit switches. And we will have limit switches here to determine the motor's location. And how does it work? Well, there's going to be a knob on the gear, and when it hits a lever, it will trigger a switch to send a signal to the computer. This signal allows the computer to know the angle at which the mirror is at. And the limit switch mechanism acts as a reset for the system so that the motor's position is always accurately known. Moving to the right side, you can see a transparent view into the prior mentioned electrical box. And as Dante said, it will be mounted to the side of the support structure. Housed within this electrical box will be the system's computer, which will be an expressive ESP8266, as well as an individual motor driver for each rotational device. We've elected to use the expressive ESP8266 as our computer for its low cost, modularity, and ability to connect via both Wi-Fi and Bluetooth. The noteworthy technical specifications include 2.4 gigahertz Wi-Fi connectivity, Bluetooth 4.3, and a 5-volt DC power. These features will allow each module to communicate wirelessly with the central router to receive the appropriate signal to determine their respective positioning. Moving on to the motor driver, we've decided to use the ULN 2003 stepper motor driver. with a built-in controller. And this stepper motor driver will regulate the operation of the rotational device. And how does this work? Well, the expressive sends a signal based on the given program to the driver. It then converts the pulse signal to a current, and that is delivered to the stepper motor. The amount of rotation delivered by the stepper motor is proportional to the number of pulses, and the speed of the motor is proportional to the speed of the pulse frequency given to the driver from the computer. And now I'll turn it back over to Kevin to tell you a little more about our protective casing.
Protective casings became a subsystem when we realized that operational lifetime within the environment present would be a key factor. One of the customer needs was that the operational lifetime must exceed 20 years. Another thing that it mentioned was the computer systems and automation, which we realized we had to keep safe from the outside elements, which led us to make a separate box for all the elements but the individual limit switches. So going into the design, we created a angled ABS plastic vacuum molded casings. And we did this for a couple of reasons. The first of which is easy and cheap manufacturing. The ABS plastic has a high max working temp of 220 Fahrenheit, and there are UV resistant pigments that can be inserted in the plastic to help it last within the desert climate. From this, we've estimated a lifetime of 30 plus years for the plastic casings. We considered other materials for the casings, but there are a couple of reasons why we didn't go with, say, carbon fiber, 3D printed materials, or metal. And the main ones were cost, as well as the heat that could be transferred through. So we used standard bolt fastenings to attach the casing to the platforms below. And the top casing slides over the shaft and it hinges on the top seam. And the bottom casing splits in half for easy access to the motor and gear systems. So here's an exploded view of how the casings would attach to the platforms below. It is fairly simple. The reason we went with angled casings was for a little bit more wind resistance, as well as structural integrity. So the two main issues we faced with the protective casings were heat transfer, making sure that the components inside were not suffering too much heat, and also the protectability. We assumed through the seal that the casings would protect the components, and Connor Duffy is going to go over how the heat transfer worked out for the casings.
Thank you, Kevin. Yeah, Kevin just mentioned the reason we chose ABS plastic. One of those main reasons was the fact that the heat transfer between an ABS plastic and, let's say, a metal protective casing, the motor is going to be working hard inside this protective casing, and you want to make sure that the motor doesn't heat up too much. And as you can see, the maximum surrounding temperature to ensure that our stepper motors remain functional is 212 degrees Fahrenheit. And the hottest recorded temperature ever recorded in the United States was 134 degrees. So we use this extreme in this scenario to make sure that our motors would remain functional. And in the first set of equations, you can see we calculate the heat flux to be 13.65 watts per meter squared. And you can then use this heat flux along with the heat transfer coefficient of ABS plastic, which is 0.175, to get a change in temperature in this scenario of roughly 18 degrees. So even in this extreme scenario, inside the protective structure, the ABS plastic is only going to allow the temperature to increase 18 degrees. And this is well below what our motors need to continue to run on. And I'm going to pass it right back to Kevin to do some wind calculations as well.
So another environmental factor that we were really concerned about is the high wind gust presence in the desert. And so we created a high wind safety mode in which all of the mirrors would be returned to a horizontal orientation. And from this, we believe that this would limit the drag and the lift fact forces present. However, our major concern was that the lift and the variations of the wind could cause a lift that could tilt the mirror enough so that it could become uncontrolled. So we did a holding torque and lift calculation to see if our plate would move within these conditions. So the holding torque of the gear was found, or the motor was found to be 50.4 Newton meters, and that's including the gear ratio. However, it's likely higher because we used a worm gear. And then we conducted lift analysis on the flat plate at 90 miles per hour, which is the highest recorded wind speed at this location. And so we have a coefficient of lift of roughly 12 degrees, which is around for a flat plate where when installed. And our assumption was that the variation in attack angle of the wind would not exceed this number. We then calculated the force from lift and then the torque acting on the quarter cord, which we found to be 40.47 Newton meters. This was less than our holding torque. So we can assume at the high wind mode, the mirror is not going to shift out of location or become uncontrollable, which is great for our design. Now I'm going to pass it on to Matthew Liffrig to discuss the costs associated with our design.
Thank you, Kevin. Now that you guys know about our unique features of our design, you have to be wondering how much it costs. First off, there's a lot of different ways to estimate cost. We've elected to use the engineering build-up cost method due to the fact that it's the most accurate. Our total cost is $491.73. We know that this is a little bit over budget, but we've broken it up into 6 different sections. The first 3 are shown on this slide, and the next 3 will be shown on the next slide. Our cost distribution is displayed in a pie chart in the bottom right-hand corner. First off, I'd like to start with the OTS parts. The OTS parts are pretty expensive due to the fact that we selected stepper motors rather than servo motors. We made this decision based off the fact that we want to have a holding torque. This system needs to be able to run in windy conditions, and the holding torque holds the mirrors in place and makes sure that they stay focused in the position that they need to be. In addition to that, we also have to purchase 8 motors. This is because we have a modular design, and each module of each heliostat module moves individually and can point in different directions if necessary for the utmost accuracy. Finally, moving over to the OTS parts, our worm gear is a modified OTS part because it is cut in order to reduce the space used within the protective casing. Now to raw materials. The raw materials are pretty expensive due to the fact that we have 4 separate modules. So our support structure is pretty large. This is also made out of steel, which is a fairly expensive material, but we chose to do this based off its strength. It should be noted that if you were to do the price per each module in the heliostat, our cost would be a lot closer to the need statement. Secondarily, our module can definitely fit larger mirrors. We've selected our mirror size based upon the need statements, but our design is robust enough to fit bigger mirrors, and that would reduce the cost per meter squared. Finally, some of these costs could probably be reduced if items were purchased in bulk rather than individually. Now I'm going to pass off to Connor Duffy to summarize our design.
So at the end of all this, we wanted to give you a brief summary. And basically, when we were designing this heliostat model, we wanted to keep a few key components in mind that would set our model apart from the rest of the field and make it a little bit unique. And the first of these things being the modularity of the design. So the first thing we wanted to do was to keep this design very easy to manufacture. And this is ultimately because of the materials that were chosen and the orientation in which all the subsystems interact and connect within the 4 subsystems that come together. And this somewhat goes hand in hand with being the design being very easy to assemble as well. As you can see from our design, there are 4 identical heliostats present on top of the support structure. And most of this design, or the design assembly, can be done before it's even in the field. And this also leads to the fact that this model is quickly assembled, as you can see in the bottom right there. It can be noted that throughout the entire design, the same screw heads are used. And this takes a lot of the complication out, as this is something you can consider to like not carry as many tools out in the field. They'll go a lot quicker. You don't have to lug as much stuff out there. And these screws are also not like at weird angles. They're very easily present on the outside. So what you are having to assemble in the field is going to end up being very easy. And as kind of we just talked about the costs and all that stuff, a lot of this goes into the lifetime of our product. The price is somewhat expensive, and this has a lot to do with the fact that we designed our entire heliostat model to be extremely durable. And the materials and specific parts that we use within our model are somewhat over-engineered to an extent, but we feel that this will ensure to extend the lifetime of the model, and also the fact that you're not going to have to go out into the field and do a whole bunch of number of repairs, whereas if we use plastic gears, stuff like that, a lot more stuff can break. And as a result of this higher lifetime, higher durability, the fact of the matter is that we have a higher factor of safety to go along with this. As we stated earlier, the heliostat won't have any problems with heat transfer. It won't have any problems with wind, especially loads. But that all went into the durability, and that's why our model is a little bit more expensive. And then the last thing that I wanted to touch on is that there is minimal interference between all 4 of the heliostat models. As you can see, once again, they're all lined up, kind of coordinated in the same orientation. And when they're rotating, they're going to be rotating about the same 2 axes. And when this happens, this is when it's maximum, we're achieving maximum power. And then after that, that's going to be everything for us. And we're going to take questions at this point.
Hey guys, this is Tom Singer from Northrop Grumman. What was your customer need on cost?
So the cost limitation was that the goal was 100 per meter squared of reflective surface. So.
And what are you at?
One more time.
What are you at?
We're at approximately $500.
$491.73.
That's pretty pricey. And if I remember from your diagram, I believe you were showing 8 individual motor controllers for each of the individual motors, and in your cost estimate, you had 1, I believe. So that adds another. I think those were $20, $16 a piece or so. So that's going to add another $100 or so to your cost, right? So you're way, way, way over your customer target. So let's talk about how you got there. You've got 8 degrees of freedom in your system, right? So each of your 8 individual mirrors, or 4 individual mirrors, could be pointing at 4 individual suns, correct?
Yes.
How many suns do we have?
We have 1.
Right. So why are we controlling 8 individual mirrors with 4 individual mirrors with 8 individual motors?
All right. So the thing we prioritized was modularity, and within the customer needs.
Well, that's what you prioritized, but your customer prioritized $100 per module, and you're 5 to 6 times over that.
So
at some point, you got to say we're not even in the ballpark of what our customer is asking for. How do we get there? And I think one way to get there is to get rid of probably 6 of your motors.
No, we completely understand. If we were to, try and make that cost, I think that's something we could easily do. The thing that we were focusing on was heliostat number, which was relating to the customer need that dictated that the design must include 4 to 16 heliostats. So we're
but that doesn't say they have to be individually controlled.
So based off of the document we got, the individual heliostats showed individual degrees of freedom. So that was an assumption that we made going forward, because otherwise, in our mind, there was no difference in 4 heliostats or 4 mirrors versus 1 mirror of 1 meter squared. We thought the difference in the modules and the number of heliostats was the degree of freedom. Certainly with our design lineup, we could have had, say, 1 motor, even with the 4 motors up top, to control the azimuth tracking. Whereas other groups may have prioritized price, what we did first was address all the customer needs, including the modularity, which we had made the assumption that could have been wrong, that it must include 4 individual heliostats. And from there, we tried to make the design as cheap as possible to meet that. But as you're obviously probably familiar, having 8 individual motors and 8 individual gear mechanisms was very costly. Going forward and not addressing this customer need, I think we would have a similar design, but larger mirrors on this same rotational device. And I think we would be much closer, maybe not at that $100, but we would be much closer.
Let's say you got rid of your mirrors, right? So, I'm sorry, of your motors, right? So you cut your motor cost. They were about $15 per motor. So even if you get your motors for absolutely free, right? You're down to like $450, right? Or I mean, you're
Our
still
gears also
even without your
cost us
motors,
roughly $150.
Yeah, I mean, you're just way out of bed with your customer's expectation. And you know, if your customer could build 4 heliostats for the price of one of yours, they're not going to go with your design, right? If you can't even get in the ballpark on cost, you're dead in the water. I mean, there's almost no capability you could provide to your customer that would justify a 5 times increase in cost.
No, I completely agree with you. That is very fair.
Okay, so that said, I'll move off cost. I'm a structures guy, and I greatly appreciate that you showed a shear moment diagram when you were doing your analysis of your beams. So I like that. The problem I have with what you did there was the loading situation, right? So you analyzed for load of your heliostats, or for the weight of your heliostats. But I'm pretty sure that your heliostats have big old mirrors on them out in wind, right? And so that's going to load the structure probably a lot more than what your weight is loading your structure. Is that right?
Yes.
All right, so we can't ignore that as a load case. So I would want to see that for sure on your structure. You had mentioned that you put some effort into making your housings a little more aerodynamic. I would suggest that is probably also not particularly beneficial when you've got a big old sail floating above these things, right? So any effort in making housings aerodynamic is wasted effort.
That's understandable. As far as the the sail and the calculations on the support structure itself, we're not as familiar with aerodynamics, and so what we did was try and analyze the system to what we could, and then build up the system to a capability that we thought could withstand the forces present. Obviously, there are a lot of further analysis that I think we could conduct in long run that we will look into.
Yeah, I'd say that's a pretty big miss in terms of the structural analysis here.
Okay. Other questions from our panelists?
Not entirely a question, but for me, what I saw in the design of your casing more than aerodynamics was that the draft angle would make it easier to manufacture. Was that a consideration that someone nudged you towards, or not so much?
Not as much. Really glad that it worked out that way, though.
And I guess I should say, I couldn't really see it in the picture, but I am happy that you included limit switches on all the axes. Yay.
Thank you.
Small celebrations. Yay. Okay. Oh, Brad, go ahead.
Yeah. My concern is kind of the uncertainty with the elements in the environment. Given the height of the heliostats above the ground, it looks like they're pretty close based on the total height. So I think sand erosion or kind of the constant wear of sand on the plexiglass might be an issue. And then as far as just kind of the sand and other particles getting into the enclosure or into the ball bearing that's exposed on top, it looked like I wasn't sure the ball bearing that was shown on the lower motor assembly looked like it was exposed through the casing. Maybe it is actually covered, but it looked like it was exposed. Is that open to the elements, or is that covered?
So the bearing itself would be exposed. We were hoping to get some watertight bearings to help us with protection.
Okay, yeah, based on the CAD, it looked like it was wide open. So
Yeah.
not just exposed, but also the balls within the ball bearing were exposed. So that's why it kind of stood out. As far as the ball bearings go, were they looking in the CAD? They looked expensive, but then I saw in the cost estimate, I think they're $1.39 a piece. So, are those, what type of material are they, and are they really $1.39 a piece?
As far as ball bearings, we don't know the exact cost because we have to buy them in bulk. The ball bearings within the CAD are from SKF because they have CAD available for specific sizes. We were hoping that we would be able to use cheaper ball bearings because there is no high speed or high loads really subjected to these bearings. And so we discounted the bearings from, say, the higher cost bearings because of our needs.
Could you do the same thing with bushings, since it is not a high speed application or high cycle necessarily?
So I think we might be able to do the same thing with bushings. Our concern with bushings was wear, being that there was, you know, a long period and the elements present. We didn't really have too much familiarity with it, so we decided to go with the option that we knew could last that amount of time. I'm sure, you know, a complex analysis might yield that bushings were the correct answer. We did consider both, but ultimately we went with bearings.
Okay. Was there analysis done for how deep or the height or depth of the pillars, and also the height of the assembly as well? What thought went behind that as far as what your final height was for your assembly?
It was pretty nominal. We wanted to give us a little bit of clearance from the ground. We did moment calculations based off of simple winds. We didn't include that within our presentation, but it is in our final report. But we didn't have an experimentation or anything to show the exact distance that the mirrors, you know, might have to be placed. So we kind of had to account. The good thing about it is that, you know, this is a prototype, and with experimentation, our design can very easily be lifted to higher heights if required. The strength of the wedge bolts that anchor it into the concrete is very high. So we don't have too much concerns about the moment or the forces acting. And we're fairly hopeful that if the analysis is conducted and it does need to be higher, that our system can account for that.
Okay. And then what about the spacing between the mirrors as well?
So
Was there
spacing somewhat minimal, just because we wanted to make the overall size, which was a customer need, as small as we could. Because each of the mirrors would be rotating in very similar axes, we didn't have as much clearance because, you know, they'd be in a similar orientation, as to say, so there wouldn't be as much interference of the actual parts. So it was a combination of making sure there was enough clearance for the mirrors, as well as trying to minimize the overall size.
Okay. And then you were mentioning the 4 to 16 requirement for the number of units. If you were to go beyond 4, what would that look like? It sounded like you're trying to make it easily expandable. Would it just get longer and you'd put more on it, or?
So the other limitation was the 1 meter squared. So I think when you move towards, say, 16, you're looking at very small plastic parts and possibly cheap servos. The issues that we ran into when we considered these designs is that with the cheap servos, to say, you don't have as much tracking accuracy. And additionally, within the environmental constraints, we were concerned that the smaller meters might run into failure. The other issue that we face is these smaller designs would most likely be composed of a lot of smaller plastic parts that would be 3D printed or possibly injection molding if we have the bulk. And with that, you have a lot of manufacturing time. Ultimately, we thought that the most efficient method would to be go really as large as possible, which, as you see, most teams went with really one individual module. We went with 4. And we did suffer, some higher costs. We think that, at 16, to have the stability in the lifetime of our module, it would be even more expensive. And so that's kind of why we settled on 4.
Okay. Thank you.
Thank you for the questions, though. Yeah, those are insightful.
Okay. We're actually right at the end of our prescribed time. It's 4:45. So might have time for one more quick question before we wrap up. If anyone's got something really pressing that they want to ask the group. Nope. Okay. Looks like you guys are off the hook then for additional questions. So we'll wrap up there. I want to thank you guys for a semester's worth of hard work and sharing your design with us and providing this excellent presentation this afternoon. For the panelists, we are, at least for today, done. We've got Thursday and Friday pretty much presentations back to back all day with a couple of breaks built in. Let me just make sure. Let's see, hang on. It's going to take me a little while. I think we're starting tomorrow morning at, let me make sure I've got the time right. Yeah, it's going to be, I think 9:15 tomorrow morning. And we'll start with the aero designs, the aerospace oral presentations, and then we'll intersperse additional mechanical presentations in with the aero presentations. And so we're going to have Professor Ting Dong in tomorrow morning to explain what the aero project was, to give us kind of an overview of that before you guys jump into those oral presentations. So we'll see you guys tomorrow morning for that. We definitely appreciate your time and service throughout this week. And excuse me, more than halfway to the end now. So appreciate you guys' time. So, okay, with that, let me stop recording.